تساوي سي تساوي سي تساوي زيرو التيار صار زيرو معناها تصير اوبن بدون التيار
of a inductor capacitor circuit, resonance circuit, is in an oscillator. Now, it is not part of this course to give you actual circuit diagrams. We don't actually go into the circuits and the way the circuits work. We're just going to discuss them in a general way. I'm not going to do through all the different types of oscillator, etc. Can you just excuse me for about 5 minutes? I've just got to go up and see an oscillator to work. As you know, an oscillator has an output, but unlike an amplifier, it doesn't need an input. How do we achieve this? If you remember when we were speaking about feedback. Yes, if we use enough positive feedback, and it doesn't have to be very much, we get this output. So we need positive feedback. That's part of the condition of an oscillator, for an oscillator to work. Feedback. So whatever circuit you see in a diagram, you must look for your positive feedback path to see what's happening. Secondly, there must be something in the circuit that's going to determine at what frequency the oscillator is going to oscillate at. Okay. So there must be some circuit, part of the oscillator circuit, that determines the frequency. For example, we could use an inductor capacitor, parallel, which is a tuned circuit.
Yes.
That's quite a common type of oscillator. So there'll be some sort of frequency set circuit. For example, not all oscillators use tuned circuits, but resonance circuits. But since we've just talked about resonance circuit, that would be a good example. These two conditions. There must also be some control on the output. Output level control. Three basic conditions. The reason for this output level control is that with positive feedback, if you remember the formulas that we used, you only need a very small amount of positive feedback to get an oscillator to work. Can you remember the formula we used for positive feedback?
Positive feedback.
The closed loop gain.
I think V out will be...
With the formula we used, remember, for where we used the open loop gain, alpha over 1 minus alpha beta, wasn't it? That's right.
Yes.
Now, if you have a very high gain amplifier, then beta doesn't have to be very big before this becomes 1. And 1 minus 1, of course, is 0, which gives you an infinite gain, which is the conditions for an oscillator. Anything bigger than that, and what you do, you overdrive the output. So you distort, in other words, your signal. So there has to be some sort of level control, the output level control of the output. Again, we're not going to actual circuits, but this will be part of the oscillator. These are the three conditions for an oscillator to work. If your oscillator used a resonance circuit, then the frequency of the oscillator can be found from the values of inductance and capacitance. Now, we didn't actually do an example of this yesterday, but we may as well do one this morning to show that we can do it. So let's say this circuit here is part of a more complicated circuit, which is an oscillator. And the output of the oscillator should be a sine wave, a nice sine wave. The frequency of that sine wave depends on the resonant frequency of these two components. Now, if I give you the values of these components, you should be able to calculate for me what the output of this oscillator would be. For example, let's say I have an inductance of, say, 10 millihenries, and a capacitance of, say, 5 nanofarads. Quite small values. Can you work out for me?
The signal is supposed to come outside the inductor and the capacitor.
Not necessarily. It depends on the design of the oscillator. I haven't gone into the details of the design. As long as we're using an inductor and capacitor.
Isn't the oscillator is going to create a lot of harmonics, and we are going to use one of those harmonics?
No, that won't create harmonics, providing we make sure that our level is correct. The only time you generate harmonics is if your output signal is not a sine wave. For example, if we overdrive this, the oscillator, then what happens is we cut off, right, like that. Now this cutoff here will produce harmonics. But if we don't overdrive and we produce a sine wave, we won't produce any harmonics. When we talk about the resonant frequency of an LC circuit, there is only one frequency, one sine wave at which it will be resonant at, no harmonics. And that's basically what we can use to calculate. Okay. The only time you produce harmonics is if you get a non-sinusoidal output. Then you will generate harmonics.
Number of cells? How many farad?
5 nanofarads.
And L?
10 millihenries. Milli and nano. So you need to know what those mean. Can you all remember the formula for this? For resonant frequency? We mentioned it yesterday. And it's the same formula for an oscillator, if you're going to use it. Resonant frequency. That's right, 1 over 2 pi times the root of L times C. So the first thing we're going to do is find out what the L times C is. Take the root, multiply by 2 pi. Reciprocal of that will give us the resonant frequency of this oscillator. My calculator out.
22.5.
Let me just keep the answer to yourself for a moment, because I want everybody to work this out. The first answer is not necessarily the correct one. If you have a calculator, it's very much easier, of course, particularly if you have pi on your calculator, which most people don't have. And you have a root. Okay, anybody answers now? Any more answers? Yours was 22.5.
22.5.
What?
Kilo.
kilo. Okay.
Special calculator on it.
Does your calculator have root on it? If it doesn't have root, it's a little bit more difficult.
Yes.
This is the handy thing about calculating with root. Actually, in an exam, again, if you've got a question like this, it'll be quite simple and it will be multiple choice, so you can at least get an idea of approximately, and then choose the one that's closest if you haven't got a calculator with a root. If you've got a calculator with a root, it's a lot easier, of course, and reciprocal. If you've got a reciprocal as well, that makes it easier. But basically, you're multiplying 2 pi and then the root of LC. Now here, of course, we've got 10 milli, so you've got to understand.
10 to the power minus.
Yeah, it's really 10 over 10 to the power 3, isn't it?
Yeah.
And of course, 5 nano is 5 over 10 to the 9, yeah. Now there's 2 or 3 ways you can do this. You can first of all multiply these two together, which is 10 to the power 12, isn't it? And the root of 10 to the power 12 is 10 to the power 6. So if you wanted to make it a bit easier for yourself, you could say this is equal to 10 to the power 6 over 2 pi times the root of 10 times 5 is 50. Would you agree with that? That's the same thing. Or you can do it simply punching all the numbers into the calculator and then taking the root times 2 pi and then taking the reciprocal of your answer. Either way. And the result of this, if you work it out, is what? Ahmed, what did you get? What's the answer to this problem? Do you have a root on your... You don't have a root? Notice 10 millihenries and 5 nanofarads. These are quite small values, aren't they, of components? And yet even with these very small values, is this what we would call a radio frequency, do you think, that we would normally use? No, it's not. It's very, very low, isn't it, for a radio frequency? Could be used by special application, but certainly not by everyday use. So this is a very low frequency. So if I wanted to make this tuned circuit oscillate at, say, much higher frequencies in the HF or VHF band, for example.
Make the components
So
lower.
yes,
Lower.
I need to reduce the values of both components. Notice both of them, both L and C, are inversely proportional to frequency, aren't they?
Yes.
So by making either or both of these components smaller in size, smaller in value, then you will make this frequency bigger. So you can understand that if we're talking about VHF or UHF frequencies, the values of L and C become exceptionally small, don't they?
Yes.
Very small indeed. You're talking about perhaps picofarads? What's a picofarad? I don't know. Minus 12, yes. Or 1 millionth of a farad. Very, very small. And maybe microhenries, or smaller, in order to give you these minus 6, in order to give you these much higher frequencies. Do you follow that? Now, there's a little point about this. Before I continue with the oscillator, there's just one thing which I've just suddenly remembered now, which I didn't tell you yesterday. Remember yesterday just a little bit of revision here. Yesterday we were talking about the band pass and band stop filters, right? Now, band pass and band stop filters. I'll just
decrease
the values. Yes, this here is 22.5 kilohertz, isn't it? Which is really like the higher audio, isn't it, really, just above the audio band. So really that's too low for us. If I really wanted to make a practical radio frequency circuit, I would need to use much smaller values of L and C. We'll do some examples of this in a minute. All right. Let me just go back a minute to what we were talking about yesterday. First of all, I gave you a circuit like this. What type of filter was this? Band pass. And in a band pass filter, we had a sort of diagram, something like that, a graph, something like this, where this is the resonant frequency, wasn't it?
Yes.
And this is the output. And if we were going to measure our output as power, then at a certain point, the half power point, we had two frequencies. We'll call that F1 and F2. The bandwidth of this, the bandwidth of the circuit,
Between F1 and
yes, it's really the difference between these two, isn't it?
Yes.
F1 minus F2. Or F2, I should say, minus F1, the way I've drawn it here.
Yes.
That would be the bandwidth of the tuned circuit. Now, yesterday I didn't give you any formula to calculate that bandwidth, did I? Okay, now what I'm going to talk about today is something called Q factor. And we can talk about Q factor of a tuned circuit or resonant circuit. And the Q factor of a tuned circuit or resonant circuit is actually equal to XL divided by R.
Parallel or in both sides? Series?
It doesn't matter series or parallel. But normally this would be a parallel circuit, because after mentioning series, most of our work is going to be on parallel. And this is what you will see mainly in circuit diagrams, are parallel tuned circuits. Now it's important to understand what this resistance is. This resistance is the resistance of your tuned circuit. In other words, it's not this. It's the losses, shall we say, here.
Z.
No, not Z. Z is the combined impedance of the tuned circuit. R is resistance. In other words, the coil of wire, the resistance of the coil of wire. Okay, anything that dissipates heat is represented as a resistance. So this is where it's reactance divided by resistive losses. Or I'll just make it simple, resistance of the LC circuit. So, in my examples yesterday, I ignored this resistance. I said there wasn't any. I just said it was an inductor and capacitor, that's all, alas. Here, we've got to think about a practical case. In practice, you're going to have resistance in the coil of wire. You're going to have resistance in the connections, etc. And you might have some losses. And anything lost, any power loss in there, this heat, appears as resistance in the circuit. The ratio of XL over R is called the Q factor of the circuit. Reactance divided by resistance of the LC circuit. This is not the same resistance as this. This is something different. This is just of the tuned circuit. I didn't mention Q factor yesterday. I should have mentioned that, but I want to make sure you understand that before we continue. Q factor. That's what it is. And the bandwidth of our filter is proportional to 1 over Q. I'm not going to give you the full formula, but I'll just give you this simple 1 over Q. Inversely proportional to the Q factor. The bigger the Q factor, the narrower the bandwidth.
Yes.
The narrower is going to be the bandwidth. Notice I take XL over R. Does it make any difference if I took XC over R?
No.
No, because XL is equal to XC at resonance.
Yes.
This is an important point. You can take XC or XL, but it's just conventional. We choose XL. That's
Here,
all.
resistance of both the circuits are.
R is the resistance of this circuit here that I didn't mention yesterday.
Yeah.
It's the resistance of this circuit. Because of the windings of the coil, perhaps, and the connections and losses from the circuit, perhaps, through radiation or whatever, that introduces a certain value of resistance in the circuit. And it's this R that we're using here, not this. That's part of a filter. It's this R which applies to any tuned circuit. So any tuned circuit at all, you can say it has a certain Q factor.
So that R here is not resistant.
It's not a resistor, it is resistance.
Resistance.
Yes. Of the coil of wire, capacitor, connections, perhaps losses through heat and radiation. I'll talk about that in a minute as we get on to radiating. All the losses of the circuit are. Normally this is, for a tuned circuit, should be very small, the resistance, compared to the reactance. 100 to 1 is a good value of Q factor. In other words, where the reactance of the coil is measured in ohms, divided by the resistance, which is also measured in ohms, maybe this is 100 times bigger than this. So it gives you a Q of 100. Now the bandwidth of the circuit is inversely proportional to Q, or proportional to 1 over Q. In other words, I could draw here, for example, a little graph, and I could give you 3 tuned circuit graphs, one like this, one like this, and one even like this. I'll draw them in different colours. Yeah. Now, they're all the same resonant frequency. In other words, if you take the L and the C and do this little formula here, you'll end up with exactly the same answer. But we can see they're different circuits because they have different bandwidths. Which of these 3, the green one, the blue one, or the red, which one would have the highest value of Q?
The
The red.
Yes.
That's right. The red would have the highest Q. This would be a high Q. That's right. Narrower bandwidth, higher Q. That's right. Exactly. So this would be a high Q circuit, what we call a high Q circuit. This would be, say, medium Q, this blue one. And the other one would be a low Q circuit. And this one low Q. Now, I'm not going to go into the math involved here, the exact math. Just as long as you recognise that the bandwidth of the tuned circuit inversely proportional to Q. So in this example, the red would be high, blue would be medium, the green would be the low Q. But all of them exactly the same resonant frequency. No difference in that. It's part of definition of our resonance circuits. As long as you have an idea what it means, and this inverse, if somebody gave you 3 different diagrams, you should be able to tell which one would have the higher Q factor, which one the lower Q factor. That's all. We don't actually need to go into the actual calculations here, that's not necessary, just the proportional.
It's only resonance over Q.
Sorry, it's reactance over resistance, yes. There's actually a little bit more to it than that. It is proportional to 1 over Q, but 1 over Q itself is not a frequency. You see, bandwidth is a frequency, isn't it? So you'll need to know your resonant frequency.
So it's at resonance over Q.
In a plain circuit, you're talking about just a straight plain circuit, FO over Q. As I understand it, it's Q factor can be given as a different value for F1 and F2, and then you take the difference between them.
F1 and F2 is
Like, for example, if you have, if you take your formula FO over Q, you see, the problem is this. If you take FO over Q, that's at resonance.
Yeah, you get
Now,
one frequency.
that's true. And it will give you an approximate answer, but it cannot give you the exact answer, because as soon as you go off resonance, you change that formula a little. It's only a small amount, but you do change it by a small amount. I can't remember the percentage now, but it does change, because XL is no longer the same at resonance. XC changes, XL changes. And so it does change a little bit. I wasn't going to give the formula FO over Q because of that.
But
If you wish to use it over Q, but the only time we're going to use a circuit with a certain bandwidth is if we're going to see what happens to the circuit at different frequencies. In other words, what happens to the circuit if I put that frequency, if I apply that frequency to the circuit? What happens to the, you know, now we're no longer operating the circuit at its resonant frequency. We're off resonance, only by a small amount. For very high Q circuits, that formula would be about right, because these frequencies are very close to the resonant frequency. For lower Q circuits, it's less accurate. But I'm not saying it's wrong, it's just that I didn't want to give it here as an absolute, because, or for a start in this course, it wouldn't be necessary. We don't need to know the formula. All we need to remember is it's inversely proportional to Q. That's the reason why I didn't give that formula. But as a quick calculation, you calculate the bandwidth as FO over Q. In other words, 1 over Q times the resonant frequency. This is FO. But I've not seen any questions like that in a test to calculate these bandwidth. Bandwidth of say a filter or tuned circuit. Okay, but in radio we need some very small values of inductance and capacitance. Very small values. So let's have a look at what they actually do in practice here. For sort of medium frequencies, they might place an inductor as a coil of wire on a plastic form, a small thing about so big, right? A little plastic tube, and around the tube they'll wrap some turns of wire. Okay. And that will be the value of, that will be the inductance, just a few turns of wire, that's all. You can tell by that it's going to be quite a small value of inductance, isn't it? But what happens when you have an oscillating current or an alternating current flow through an inductor? It produces a magnetic field, doesn't it? Sometimes in the middle of this tube they have what is called a slug. Not very good at drawing this, but which has a thread on it which when you turn it goes into the tube. That slug is a magnetic, or has an effect on the magnetic field. It can increase or decrease the amount of magnetism and therefore change the value of L. The circuit symbol for that sort of thing would be something like this. If you saw it on a diagram, we'd have a little line through it to show that it is a variable inductance. Right, so you can change the value of inductance by a small amount. Why do you think it's necessary to have to be able to change the value of L?
Just exactly at the frequency you
That's
want.
right, to get it exactly right. I mean, when they design these circuits, they want an exact frequency here. So instead of just getting fixed values, making one of them, or maybe even both of them, to a certain extent, we could do. But very often it's the inductor that's changed. So that they can adjust it, right, to an exact value of L, to give them an exact frequency of oscillation or bandwidth or whatever. Well, usually the circuit is designed for one particular frequency. Now, I'm not talking about tuning throughout a radio band. If that's the case, a different technique could be used. You could use a variable capacitor which enables you to vary it by a large amount and therefore vary the frequency. But these are just like, what we call this preset as opposed to variable. It's a preset. In other words, it's normally set in the manufacturer, but a technician might have to change it again if something goes wrong, radio gets damaged or component is changed. Sometimes you need to check that again. Now you guys who've already done radio or anything on radio, you'll already have had some experience in doing this. Is there anything particular you need to use when you vary this?
Yeah, the signal should be not affected.
The screwdriver, yes. What about it?
Should be not affected.
Yes, it should really be a plastic adjuster, shouldn't it? It should be made of plastic rather than metal if you can do that, or something like that, or even wood. Well, I've done it with a toothpick, shaped like a screwdriver. But anyway, as long as it isn't metal. Why do you think, for those of you who have not done anything on radio, why do you think you need to use, say, plastic screwdriver rather than a metal screwdriver when you're adjusting this thing into here?
Because the magnetic field
Sorry, yes.
the current flow the magnet to be
Current, well, basically, if you put a metal in there, the magnetic field is going to, the metal itself can affect the magnetic field, won't it? So as soon as you put your screwdriver anywhere near it, even without adjusting it, whoop, the frequency's changed. Take your screwdriver away, frequency goes back again. Well, that's no good. You're not going to be able to adjust it very easily there. So you use a plastic one, which shouldn't affect it, and then you can turn the little slug, as they call it, to set the frequency correctly. So that's one way in which we can design small values of inductance. There's another problem as well when this produces magnetic fields. As you know, the magnetic field is produced around the coil like this, isn't it? Remember? Now, for a radio frequency coil, that magnetic field can radiate energy and can influence other components in the circuit. Right? There's two effects of this. First of all, it can interfere with the rest of the circuit, which is something you don't want. That can produce a lot of problems. Secondly, it loses energy. If it loses energy, it's like increasing the resistance of the circuit. What does that do to the Q factor? Q factor goes down, doesn't it, if you increase resistance? So what they do is, they usually place this in a metal can with a hole at the top. Yes. If you've had any experience at all in radio, you'll be very familiar with this sort of thing. The metal can is like a shield, isn't it, to prevent the field. Yes, and it should be grounded as well, because it's also affecting capacitance as well as inductance, in fact. Anyway, that's a variable or preset inductor, which you very often find in radio circuits. And they would be handling frequencies up to about what's the first RF of the aerotron? 10.7 megs. So up to about 20, between 20 and perhaps a maximum of 100 megs, maybe. And lower than that, just use more windings on the coil. But what about when we want to generate frequencies, say we want to design an oscillator for, say, microwaves? Crystal. I haven't mentioned crystal yet, but actually a crystal works like a tuned circuit, except it's using quartz or what's the latest crystal types? Not quartz, is it? It's something else. And it vibrates at the radio frequency, generating a small voltage across itself in a crystal. But the problem is, with crystals, is the higher the frequency you want to generate, the smaller the crystal and the thinner the crystal. So there's a limit, practical limit, where the crystal just becomes too small and too fragile to generate the very high frequencies we need, say, for microwaves. Now, microwaves, we're talking about something in the order of gigahertz, aren't we? Perhaps. What's the SHF band?
From 3 to 30.
From 3 to 30
No. Gig.
Mega. Mega.
mega? That's the HF band.
No.
HF band.
No, I said what's the SHF band?
Oh, from
30 mega to 30.
giga to 30 gig.
300 mega to 3 giga.
300 mega
To 3 giga.
to 3 giga is the SHF band. Okay, so let's say we have a frequency of say 3 gigahertz.
No, more than 3 giga to 30 giga.
3 to 30.
Yes, an SHF band, I think 3 gig is the lower end of the SHF band. So anyway, let's take 3 gigahertz as an example. Okay, 3 gigahertz. We can actually use this formula the other way around to find out what values of inductance and capacitance we need to make such a circuit. And if you did that, you'll find you're talking about almost picohenries. The values of L and C are exceptionally small. In fact, you could get a piece of wire no longer than that, which would be sufficient inductance, right, to give you the necessary circuit for resonance. If we have a look at this formula here, this gives me the resonant frequency, agreed? But if you look at this formula, there's no fixed value of L or C that will give you that resonant frequency. If I change the value of L, you can change the value of C to maintain the same resonant frequency.
Yes.
Isn't that right? But say I wanted a circuit, a tuned circuit, which not only had a certain resonant frequency, but also had a very, very high Q factor. A high Q factor. Now a high Q factor,
Make it small.
remember IQ factor is XL over R, which is also equal to XC over R. To make XL big, what do I need the inductance to be? Large. To make XC big, what do I need the capacitance to be?
No.
Very
Small.
small, that's right. So, even though I keep the same resonant frequency, if I use a very large value of L compared to C, not large per se, but compared to C, I can make myself a very high Q factor circuit. Okay, the way they do this with microwaves is this. They get a small piece of wire, right, and they bend it into this shape. And that is a tuned circuit. That's an inductor capacitor circuit about so big. The gap between the ends of the wire form the capacitance, and the length of the wire forms the inductance. It's an equivalent to this sort of circuit, except the values of L and C are exceptionally small.
And constant, you can't.
Yes, and constant in this case, you can't change them. Now, and this is what I'm going to come to now. What they do is that, remember, Q factor means a very small value of resistance, doesn't it? To make the resistance smaller, I can connect another of these in parallel. Right? So I connect another one like this. You can imagine it just sitting behind it, like that, in parallel with it. Now imagine I connect thousands of those in parallel with one another. Then basically, imagine, now this is something, imagine I make it like this, a big block of copper, solid block of copper, and I drill a hole in it. So that hole goes right through the solid block of copper. I then machine out a gap there. So that gap runs the length like that. So it's like a keyway through the solid block of copper. Now that is a tuned circuit, and it's called a cavity resonator. Yes. Cavity resonator. This is actually a very high Q factor resonant circuit.
High Q factor.
Yes, a very high Q factor resonant circuit for microwaves. Okay, because the values of L and C are exceptionally small.
Very high.
let me just write that down. You can take this little drawing down if you wish. Cavity resonator. It's a resonant circuit with very high Q factor. Used for microwaves. Not very good at drawing this. I should give a better drawing, but you can understand if you follow what's going on there. You can think of this as a block of copper. That's usually how they're made.
What's the name of it?
I haven't given this a name, just a cavity resonator at the moment. Now I'm going to explain very briefly, because it's not really part of this course, different devices that use cavity resonators. But that's how a cavity resonator works. It's basically a tune circuit, but it's a tune circuit at microwaves. Because the microwaves are very, very high frequency, and we're using such low values of inductance and capacitance. Because of such low values, the easiest way to make it is using this block. Okay. Some of the devices that use cavity resonators in our microwave, they use a diode called a gun diode, is that right?
What?
Gun diode in the microwave? I think it's a gun diode. This stands for something, but I can't remember what it stands for. These are three devices, as an example, that use, all of these use some type or some design of cavity resonator. Of course, to make an oscillator, you need an amplifier, some active component with positive feedback, not just the tune circuit. So all these devices are actually oscillators of some description. They all work in a slightly different way, and I'm not going into details of how they work, but they're all a type of oscillator.
How do you wire this cam?
Yeah, how do you? Well, it's done actually, for instance, in these two devices, in the klystron and magnetron, it's built into a tube. Actually, it's not glass, it's metal, evacuated, and there's an electron beam that runs past these cavities. And the electron beam oscillates between the two ends of the cavity at the frequency of oscillation to maintain oscillation. It's all done within an evacuated compartment in both these devices.
But isn't there supposed to be a wire?
Well, you mean how do we take the output?
Yeah.
The output is taken usually by a little, for instance, I think in the in the magnetron is at the klystron. I think in the magnetron, or the klystron, the output is taken by a little loop of wire connected inside the cavity to an output device here. Acts as like a little antenna, like a little radiating antenna. Picks up the energy here and radiates it out here.
Where's the power connected then?
The power is connected to the cathode and the anode. Well, I don't want to go into the whole details of it. I mean, the whole thing is designed quite complicated.
It's like a block.
Yeah, but it's actually like this. There are actually maybe 10 or 20 of these connected in a circular form around a block of copper, and there's an electron beam that goes from the center here, from a cathode, and the copper outside is acting as the anode. So the electron beam shoots out towards these cavities. The cavities start to oscillate, and the electron beam oscillates between the two walls of the cavity. Quite complex. And the electron beam, actually, the electrons sort of spiral round at the frequency because of this oscillating beam. Whoever thought of this? I don't know. This was actually invented a long time ago during the Second World War for radar systems. That's when it was first used. Both these were done for microwave radar systems. This guy here, the magnetron, is still used nowadays. Where do you think they use this? Quite a high power device.
What's the magnetron?
It's a high power generator of microwaves. Right. All these generate microwaves. Right. They're generators. Whenever you see the word oscillator, it's a generator. You put DC in, basically, and you get this microwave out. And this actually is used in microwave ovens. If you have a microwave oven, you'll have a magnetron in it. Gun diodes are more up to date. They're semiconductor equivalents to these. I'm not quite sure the design, because they're usually all encased. If anything goes wrong with them, you throw it away and get another one. You don't actually fix it. But they're like a semiconductor equivalent of your magnetron and your klystron. But they're only low power output for the gun diode. You wouldn't find a gun diode, for instance, in a microwave oven. It's just not powerful enough. And they used to use these things in radar systems. Microwaves were used at 10 centimeter radar and 1 centimeter radar. Yes, actually the design of the klystron and the magnetron are quite complex, really, in the way it was designed. It's amazing it works, but it does. Smaller the values of L and C. When we get onto the microwave side of it, we have to start talking about cavity resonators. So specially designed oscillators are made. These oscillators, in most oscillators at lower frequencies, you have a tuned circuit, you'll have a transistor or op-amp or something, feedback components, biasing components. If anything goes wrong with those, you can change any individual component. In microwave circuits, the oscillator or generator is contained all in the one unit, together with the resonant cavity, the cavity resonator. If anything goes wrong with that, you change it. If you have, for example, a dish, a TV receiving dish, you have in front of the dish what is known as an LMB. Inside there is a cavity resonator. But in this case, it's for receiving, not for transmitting. Low power cavity resonator. But if anything goes wrong with that, it's basically a replacement job, isn't it? No, it should just receive. Because that's the way it's designed.
resonator.
Cavity resonator, yes. Any type of oscillator at microwaves would use a cavity resonator.
But in electromagnetic, we just tuning again.
That's not microwave, is it? Right. But if you were to go, for example, to the mast, to the microwave dish for our point-to-point microwave link, you will see in there you have cavity resonators.
Both sides.
Both sides. Only would use actually gun diodes in the semiconductor gun diodes. Quite low power, these things, though. Perhaps in the order of milliwatts. And it's the same with the receiving antenna for TV. You have an LMB which also has an oscillator in it. Although it's not a transmitter, it will have an oscillator and it will have this sort of device. But if anything usually goes wrong with these, it's a matter of taking it out and throwing it. There's not much you can do with those things. You can't fix them. You can't really fix those things. You buy them as one complete unit. You apply DC to them and you get a microwave out of them. That's the bottom line.
So fixed microwave or can change it?
That's an interesting point. Usually they're fixed. Well, yes. Certainly on our applications that we've spoken about, that is point-to-point microwave links, it's fixed. We don't have any control over that frequency.
If it's not changing.
Yes, you can't tune them, in other words. You know, this idea of, like we mentioned here about changing the value of L.
Can't change it.
Yes, you can't usually change these because it depends the way they're manufactured, you see.
Yeah.
There's not much there you can change.
The higher, but you want to Q factor is make the cavity resonator bigger.
Well, the reason why this has a very high Q factor is because the resistance is very, very small because it's drilled out of a solid block of copper. And that makes it a very high Q.
Let's make it bigger.
I'm not quite sure. I mean, they're not going to be that big. But don't forget, these holes here are very tiny, small little things. But you can always tell, you know, they're reasonably heavy, even though it's a small block. It's quite heavy because it is a block of copper. You know, it's not like a printed circuit board.
We'll make it bigger. We'll make the bandwidth smaller. Make the frequency higher for the.
Well, the higher to make the frequency higher, the manufacturer would drill a smaller hole, wouldn't he? Perhaps. But he manufactures these blocks to oscillate at a certain frequency. And as far as we're concerned, when we purchase these devices, whichever device we purchase it at a certain frequency, and that's fixed.
Each of them have a special value.
Yes, you would have to get the right one for the right frequency, of course, yes, for replacing. Okay. All right, let's take a break. The resonant frequency. That's when it's part of a filter. When it's used in an oscillator, it's to give you a sinusoidal wave output at a certain frequency. Now, a sine wave, of course, is a fixed frequency, isn't it? Anything that's any other shape means it's made up of more than one sine wave. It contains what are known as harmonics. But if the waveform is sine, then it's just one frequency. And that's the object of an LC tuned circuit, resonant circuit.
Or oscillator.
Oscillator,
And
filter.
what the tuning also, what we did in the radio, it was just to get.
Well, basically, that's really filtering. You're talking about the alignment of the frequency multipliers. That's filtering. Yes. Don't forget, we don't go that deep at this stage. I mean, this is not this is a telecommunications course, so there's a limit to how deep we can go at this particular stage. We can talk a long time on different types of filter to give you different characteristics, different bandwidths, etc. But we're not going to include that here. Basically, we covered tuned circuits so that we know we need tuned circuits for radio frequency generation to generate radio frequencies as oscillators. Now, in the case of frequencies in the SHF band, when we're talking about the microwave region, we use special types of tuned circuits called cavity resonators, because the normal inductor capacitor would not be suitable for too large values. The values are just going to be too big to be used as tuned circuits. So this is an important point. But those are the two main reasons why you would need to use tuned circuits or resonant circuits. Parts of telecommunication systems is the concept of modulation. And let's now consider the reason why we would need to use it. Somebody banging up there. Somebody fainted. Okay, first of all, let's consider what happens if we wanted to transmit a radio signal and the information on the radio signal was in fact our voice. We wanted to design a very simple radio telephone system. Okay? Let's consider the problems involved with that. Now, first of all, when you speak, say, into a microphone, what you're doing, you're changing your sound waves into electrical signals, aren't you? And there's a certain thing we can say about these electrical signals. We call these audio signals. Why do we call them audio?
Small frequency.
They're quite low frequency, but that's not the only reason. The reason for audio means that if they were sound waves, we'd be able to hear them. If you can hear it, it's audio. That's right. So the audio frequency range for telephones, we normally accept to be between 300 hertz and 3 kilohertz. That's right. But of course, if I wanted to transmit this signal as a radio wave, would I use these frequencies? If I wanted to transmit this signal as a radio wave? No, because these are quite low frequencies, and we've already discussed all the advantages and disadvantages of using different radio frequencies. So, in fact, these frequencies alone are no good to us. No good at all. We have to change the frequencies. We have to change this information and move it to a higher frequency suitable for radio communication. Now, what frequency we change it to depends on the band of frequencies we're going to use. For example, let's just choose an example here. Let's say I want to use VHF as my frequency of transmission between a transmitter and a receiver. Okay, we're going to use a VHF signal. If I'm going to use a VHF signal, we're talking about between 30 and 100 30 megahertz to 300 megahertz. Okay, so let's say I'll just choose an example, a VHF frequency of, say, 100 megahertz. Now this is just your example here, 100 megahertz. Now what the objective here is, we want to take this band of frequencies. Remember, when you're speaking, you're producing a wide range of frequencies between 300 and 3,000. Actually, this is about 3,600 kilohertz, isn't it? 3,600 hertz, I should say. And what we want to do is change those frequencies into radio frequencies to transmit. If I was to draw this as a frequency spectrum, this is our frequency spectrum here. Down here we have the audio frequencies, and as we go higher and higher, we get higher and higher radio frequencies. Eventually we'll reach a frequency of about 100 megahertz. So, if you think about if you were to design a simple radio system, the very first thing you would need in your radio is some sort of generator that can generate 100 megahertz. Okay? An oscillator, in other words. So let's just draw that in our simple case. The first little block here would be some type of oscillator, probably using a tuned circuit. Could be using a crystal, as we'll see later, but it doesn't really matter. The main thing is it generates our frequency, let's say 100 megahertz. So the output of here is 100 megahertz. This is our oscillator. And here we have 100 megahertz output. Now, what we do then, we put it through another stage where we mix, right, the audio, that is these sets of frequencies here, which could come from a microphone and amplifier. So we would have some type of microphone here, which goes through some audio circuit, basically an amplifier. We mix these two together so that the output, okay, is a small band of frequencies either side of 100 megahertz. So we would have here an output where we have a small band of frequencies, okay, either side of 100 megahertz. Now, how wide this band of frequencies is depends on the bandwidth of our speech. The more frequencies I want to transmit, the wider this band of frequencies will be. The process of mixing the audio with the oscillator is called modulation. It is a mixing, it is a type of mixing, but we use a term here, modulation. And there are 2 or 3 ways in which we can modulate our carrier or radio frequency to produce this band of frequencies. If we do not produce a band of frequencies, we're not producing any information. Information must be contained within a band of frequencies. Remember what we said earlier on. The rate at which you transmit information or convey information depends on bandwidth, doesn't it? If you reduce your bandwidth to 0, then you're not giving any information to anybody. So the wider the bandwidth, the more information we can give. We need a certain minimum bandwidth for our audio signal, okay, in our example here, like for a telephone channel. And so therefore we need to produce a band of frequencies. This would then go through to an amplifier and an antenna and be sent to the receiver. I'll talk about the receiver in a minute. Before we talk about the receiver, let's consider what type of modulation we have. Basically, there are 2 types of modulator. The simplest perhaps to understand is the amplitude modulator. Again, we can draw this very simply, and there are some drawings in the notes I've given you. You don't have to necessarily remember these. Where what we do is we take the carrier, that is this frequency here from the oscillator, and we change its amplitude. I'll just something like this. And we change its amplitude according to the signal that I'm using for modulation. Now, there's a much better diagram of this in your notes, but have a look at this. This wave here is our 100 megahertz signal, the carrier, what we call the carrier wave. And in my example, I've used 100 megahertz as the example here. Now, what we do when we speak into the microphone and we produce audio frequencies, we change the amplitude of that carrier according to the amplitude of the audio wave.
This carrier with the signal.
With the signal, yes, that's right. This is the modulation, the amplitude modulation. Now, it should be also in this example that I've drawn here, I've just drawn one particular audio frequency. In practice, of course, when you're speaking into a microphone, you produce a complex wave of many frequencies, but the main thing is the amplitude, the level, shall we say, of your carrier is changed according to the amplitude of your audio, whatever it is you're using to modulate. This is amplitude modulation. Okay? Now, it's not part of this course to go into exactly how these circuits work, just the result. This is amplitude modulation. And it can be shown that with amplitude modulation, if we have a look at this graph now, what we actually transmit from the antenna will be the carrier, which I'll call FC, in our case 100 megahertz, and there'll be some frequencies above FC up to a maximum, and some frequencies below FC. In other words, there's a band of frequencies we're going to transmit. Now, the next thing to decide is what are these frequencies going to be? Well, that depends on the highest frequency of your transmitted signal. So let's say the highest frequency is 3 kilohertz. Then the highest frequency transmitted will be FC plus 3 kilohertz. And the lowest frequency would be FC minus 3 kilohertz. Now, I'm not going to go through the mathematics of why this is the case from here, but it is in fact the case. This is the bandwidth of our signal. And really, the object of this course is just to introduce you to a few terms that you need to know. This is called a sideband. In fact, it's called the upper sideband. And, naturally enough, this will be called the lower sideband. And they're both equal. This, of course, is just two examples I've got, FC plus and FC minus 3 kilohertz.
The bandwidth.
That's the band. What is the bandwidth then in that case? What's the bandwidth of that signal?
The difference between the maximum
Six.
So what is it?
6K.
6K, yes. That's right, it's the difference between the highest frequency transmitted and the lowest. In this example that I've chosen here, it would be 6K, wouldn't it?
Yes.
That's true. Using amplitude modulation, this is the result. This is what we're at. These are the frequencies we're transmitting. Now, of course, when you speak into a microphone, you're producing frequencies all the way up to a maximum of 3 kilohertz. So you're producing lower frequencies as well than that, but they're all within that band. All within that band. If you remember, I mentioned also, since bandwidth is the rate of giving information, I gave you an example of a TV broadcast, didn't I? What did I say was the bandwidth for TV?
6
Very
million.
high.
Yeah, it's about 5 meg I gave you actually. Does depend, but say 5. Now that's 5 megahertz. If I was going to use this type of modulator to transmit a TV signal, then the bandwidth would be plus and minus 5 megahertz.
Yes.
10 megahertz bandwidth. That's very wide, isn't it? Very wide. In that example, if I was going to use this type of modulator. But of course, as you know, from what you've already learnt about telecommunications, more information is being given with television than it would be with just a telephone call. This is what we might use for telephone. Now the next question is, of course, that in the band of frequencies that we're using, there could be somebody else also wanting to transmit telephone calls on the VHF band. So what do we do to make sure we don't interfere?
Put or circuit, tune circuit.
Oh, well, what's the first thing that we must make sure? If say, for instance, two people want to use the VHF band,
Tune circuit.
the first thing, which is a very obvious thing, is to do what?
rejection circuit, frequency.
What are we rejecting?
Frequency
Which frequency?
that the want, the other one.
Okay, well, so before we do anything with circuits, the first thing we've got to make sure is that the other guy doesn't use the same frequencies we use. Right?
Carrier.
Right, okay. In other words, he can use the same circuit. The only difference is this guy here would be different. It's no good him using a 100 megahertz oscillator, is it? Because if he uses a 100 megahertz oscillator, he's going to end up with exactly the same frequencies that he's going to transmit on as we're transmitting on. And of course you're going to get interference. So all he needs to do, he doesn't have to change anything else. If he changes this oscillator frequency, let's say he chooses, instead of 100 megs, he chooses something up here, out of the way. Maybe this is 101 megs, just as an example. He's also going to produce sidebands, isn't he? Just the same as I am. But providing in my receiver system, I put a filter, don't I? To just select these frequencies, the filter is very important, and reject this guy, then when I receive, I will just receive my signal and reject his signal. Of course, what I've described here is frequency division multiplexing of the band. This is frequency division multiplexing, when more than one signal can use the same band of frequencies, but they don't interfere with one another, providing they, don't use the same frequencies.
At the same time.
Yes, at the same time as well, but this is what we call frequency division multiplexing, FDM.
What you can say it again, please.
This is an example of frequency division multiplexing. The idea being that you can have as many people as you want transmitting on the VHF band, providing each of them occupy a different band of frequencies.
Yes.
That's the whole idea. And the only way they're going to do that is to make sure that their carriers are different. The width of the band of each is the same. They're all, say, telephone channels.
Yes.
No problem with that. But they mustn't interfere with one another, so each one would use a different carrier. And we can get several channels, a lot of channels, in the same VHF
time and
band.
different.
Same time as well. Exactly.
Same media.
Well, we are using the same media. Now, of course, the idea is, say at VHF or at UHF, that there'll only be so many channels available for people to use. I mean, there's only so much total bandwidth, isn't there? We've got to get as many channels as we can within that band. This is the whole idea of licensing, so that you don't interfere with everybody else. But this is an example of FDM. But remember that in amplitude modulation, we produce upper and lower sidebands. The upper sideband, okay, is the carrier plus the highest frequency. The lower sideband is the carrier minus the highest frequency, whatever that is. Let me just ask you a question about this to see that you followed it. There's nothing, I'm not going to go any deeper into circuits here. That's radio, that's for the radio guys alone to do. But you must understand the principles of what we're talking about here. Let me just put a little question here. Sorry, what did you say?
Use this media, frequency division mechanism, only for...
No, I didn't say that.
This is general.
This is just an example of FDM, that's all. It doesn't necessarily mean that we have to use amplitude modulation. In a little while I'll tell you about the other types of modulation we can use. But they all have one thing in common, they all produce a band of frequencies. You see, and as long as each person transmits on a different band of frequencies, we can call that frequency division multiplexing. Let's say a transmitter on a carrier frequency of 99.5 megahertz. If the carrier is modulated by a 5 kilohertz minimum to 20 kilohertz maximum signal, that's the width, the maximum and minimum. It's not a telephone, it's some other type of signal, it doesn't matter what it is for the moment. Then what frequencies are transmitted? What comes out of the antenna? What is the bandwidth of our signal? I want you to think.
Would be, I think 100 maximum. No, not 100.
Well, there's 2 or 3 answers to this, all of which, depending on how you look at it, could be correct. The way you would answer it is something like this. First of all, you would think about your graph with your carrier.
Minimum would be
Think about your...
maximum.
This is the conventional way of drawing this, by the way. These use these little blocks here to indicate the upper. This is the upper side band, or USB. Sometimes it's just called a USB. This is the LSB. And we're using amplitude modulation exactly as I described it. Now the question is, what frequencies are going to be radiated by this transmitter?
Minimum 99.
What frequencies?
Yes, or band of frequencies. Now this is what it would look like on a spectrum analyzer. This is what it would look like if you were to look at the spectrum of the radiated signal.
Minimum
The
99.
bandwidth would be 40 kilohertz.
The bandwidth would be...
From 97.5 megahertz to 119.5.
Well, the bandwidth, just taking what you said first, you said 40 kilohertz. Does anybody disagree with that, or wait till everybody's thought about it? That's the first thing. That's probably one of the most important pieces of information we can get from this question. The question wants to know more or less what frequencies are actually transmitted. And if you think about what we said, the little rule I've given you, you should be able to put values to all these parts of our...
The carrier plus 5, minus 5. And the carrier plus 20, minus 1.
And minus 20. Yes, there's 4 different frequencies we can calculate here. 1, 2, 3, 4.
FC minus minimum, FC minus minimum.
Yes, it's the difference and the sum. So first of all, let's choose the lowest frequency. It says here 5 kilohertz is the minimum frequency.
Yes.
Nothing less than that will be transmitted
Yes.
or used for modulation. So therefore,
Maximum 20.
yeah, let's have a look at this one first, the 5 kilohertz.
Yeah.
So we know FC, we know that's going to be transmitted for a start. That's one of the frequencies, 99.5 megahertz. Isn't it?
9.5 minus.
Now this frequency
100.
Plus
is plus 5 kilohertz on this, isn't it?
100.
All right. Plus 5, no.
No. 0.005.
Not point
0.0.
5 kilohertz, yes, that's right. You don't forget your decimal points here. Which is 99,
0.05.
well, 99.5 plus 5.
0.505.
Will be 100.
05. Nah, yeah.
megahertz?
5K.
Yes.
5K means 0, 0.
Now this is something which a lot of people make mistakes on in multiple choice answers.
Yes.
They'll almost certainly give you that answer that you said as a wrong answer. Remember, this was kilohertz,
1, 0, 0.
which is 0.005 megahertz, isn't it? Change it to megahertz because we're in megahertz here. Don't get the two confused.
Why? This is the megahertz is 10 power to 6.
Yes.
And kilohertz 10 power to 3.
Bring everything to megahertz.
The half. It's a kilo is the half.
Wait. 5 kilohertz is how many megahertz?
5 kilohertz.
Yes. How many megahertz is that?
0.005.
Yes. You divide it by 1,000.
Yes.
Divide that by 1,000. You're moving the decimal place 1, 2, 3.005 megahertz. Now the reason why I brought everything to megahertz is because that's our scale. That's what we've got on our graph. So that frequency will be 99.505 megahertz. This frequency is 99.5 plus 20 kilohertz. So this would be 99.52, is it? Yes, that's right. Megahertz. Do you see that?
Yes.
The math is simpler, but don't make the mistake when you come to your indices. If you're in megahertz here, you have to change your kilohertz to megahertz. And now if we look at the lower side band of frequencies that are transmitted,
99.5.
here it's 99.5 minus 0.005, isn't it?
99.44.
Yes, 99.495. Isn't that right? Megahertz. They're all in megahertz. That's right.
And 99.48.
And 99.48.
Yes.
That's right. That's exactly right. Those are the frequencies that will be transmitted. There'll also be frequencies between here, perhaps, and here, depending on what's going on. But we're just talking about the highest and lowest, the minimum and maximum. This is our upper side band of frequencies. That's our lower side band of frequencies. That's our carrier. Okay? The math is not too difficult as long as you don't make the mistake with your kilohertz and megahertz. That's the only thing you've got to be watch out for. As I say, in a question in the test, this would be a multiple choice. It might not ask you for all the frequencies. It might just ask you for maximum and minimum. Okay. What is the bandwidth then of the whole signal?
The difference between the minimum and
99.
Yeah, it's the difference between this and this, the highest and the lowest transmitted. But in fact, to make it easier, it's just going to be twice this, isn't it? If you take this and subtract this from it, what do you get? 99.52 minus 99.48, you should get 40 kilohertz. So there's an easy way of doing that. Just take the highest frequency and double it. That's 40 kilohertz. The highest frequency, modulating frequency. The highest modulating frequency and double it. Not the highest radio frequency, of course. The highest radio frequency is this. Transmitted. Don't double that. That won't give you the... And then
The highest what?
the highest modulating frequency. In fact, the bandwidth can easily be found here. Make a little note of this.
قطع صوت يا شيخ.
For a double sideband, this is where we're using an upper and a lower sideband. Double sideband, AM signal. What does AM stand for here? Amplitude modulation, yes. Sometimes it's called AM, amplitude modulation. For an AM signal is equal to 2 times the highest modulating frequency. So you've got to find out what the highest frequency is used for modulating. Twice that is the bandwidth of your transmission.
So it's dropped only 99.48.
Yes, you can take that away from that and you should get the same answer exactly. Yes, Ali, what's the...
with the red...
This?
The top.
Oh, this is LSB
Yes.
and USB.
So
Upper sideband and lower sideband. I just put LSB and USB because that's the most common way of
that
putting it.
red ink and...
It's difficult, eh?
Ink.
I'll use different colour. Do you want me to open this a little bit?
No, what?
Does that help?
No, eh?
No.
No, eh?
Lower sideband,
Low side?
band.
Low side.
Lower sideband.
Lower
I
side.
had it written on the last diagram, didn't I? Lower side
Yes,
band,
yes.
and this one is
Higher
upper
side.
side band.
Higher.
And higher.
So often you just hear of USB and LSB. That's the usual way of...
Okay.
Now I know I'm introducing you to a lot of new terms here perhaps, but I have to do this without going any deeper as to why they... Because this is the sort of nomenclature they use. AM, amplitude modulation. If you think about your radio that you use in a car, you have different wave bands, don't you?
Yes.
Some radios out here have actually shortwave band, don't they? Car radios. Not all of them. It's not common, but a lot of them do. But they also have other bands, other wave bands. Can you remember? For instance, if you're receiving an AM signal, what wave band would you use for that, do you think? Anybody any idea?
Wait, huh?
Mm.
What is band you mean?
Wave band.
Wait.
Or what frequency band?
Medium.
Medium, yes. MF.
Because we can
Yes,
use it
Lena.
from 350 kilo.
The medium, what is the medium frequency band? In hertz, in kilohertz?
Yeah.
From
300.
300 kilohertz to about 3 megahertz, isn't it? Now, sometimes that's called the medium frequency band or just the MF band. MF. You might see the term MF written on your radio. On old radios, it might be called MW, meaning medium wave band.
Medium wave. But here we need the medium wave band. You mean the bandwidth that is in the...
No, this is, these two are referring to the band, in which radio band are you receiving? Are you receiving the medium frequency band or the HF band or the VHF band or whatever?
In this example, we're not receiving this because very high frequency here.
Oh, this example's different, yes. I'm not talking about this example.
No,
Because this example I've chosen is actually in the VHF band, isn't it?
Yes, that's
But what I'm saying is, in your radios, you will see the MF band, or sometimes it's called the MW band, but the MF band is the more common. And in the MF band, the type of modulation used in the MF band is nearly always amplitude modulation. Or sometimes they therefore refer it to the AM band. But in fact, there's no such thing as an AM band. AM means the type of modulation, amplitude modulation. Now, the example I've given you, this example here, is not the AM band. This is in the VHF band, isn't it?
Yes, yes.
It's VHF. 99.5 megahertz is a VHF frequency.
Yes.
But on your radios, particularly if you look at your car radios and see your bands there, if you've got a medium frequency band, sometimes they'll have AM written on it as well. Meaning that when you're receiving signals in the broadcast, because it's designed for broadcast transmission. The type of modulation will be this type of modulation, amplitude modulation. Okay? Sometimes it's called double sideband amplitude modulation because we're transmitting both the upper and lower sidebands. And this is what happens when you amplitude modulate your signal.
It's in the radio, FM.
That's a different type of modulation. Yeah.
The SW.
And sometimes you see shortwave, yes, which is HF.
Frequency modulation.
Yeah, I haven't talked about that yet. So. But there's a different type of modulation, not like this. You can't use these, you
The
know.
idea of the amplitude modulation is make the bandwidth
بطريقة ثانية.
channel
بطريقة
can
ثانية.
let more go more, can let more less.
Well, in any type of modulation, whether it's amplitude or whatever, the idea is to restrict the highest and lowest frequencies. Just try and restrict them. That's true.
هذا كله عشان الباندويث هذا؟
You must be able to. That's the reason why when you tune your radio, you get different as you tune the radio up and down the band, you get different signals coming in. But there should be only one at a time. Occasionally you might get some interference, but it shouldn't happen. You should only receive one signal at a time. Each signal will be modulated like this, more or less the same band of frequencies, but at a different carrier. And that's what you're doing when you're tuning your radio. You're selecting, by using a filter, different set of frequencies. Why it's called that? Because what we actually transmit is an upper sideband, a lower sideband, and a carrier with carrier. And what is the maximum bandwidth? Well, the maximum bandwidth is 2 times the highest modulating frequency, isn't it? So in this particular type of modulation, the maximum bandwidth is 2 times highest modulating frequency. I'll just put mod F there because I've already described it here.
For the lower sideband, the bandwidth
Right, now the lower sideband,
will be 15.
yes, what you've got to do to find the bandwidth of a lower sideband by itself, we'll be talking about that in a minute, is really the difference between the highest and lowest modulating frequency, isn't it? Which would be 15 kilohertz in that example. But we'll talk about that in a minute. In the normal,
between for double side band.
this is the same.
The same.
Same as this, exactly, yes. I haven't, this is, what I've described here is this. Now I'm going to describe a slightly different variation on AM, slightly different types of AM.
Can you write the meaning AM?
Amplitude modulation, AM. In fact, let me just head this whole thing and call it amplitude modulation. Amplitude modulation is the type of modulation we're talking about here in all these examples. Double side bandwidth carrier, the bandwidth is 2 times the highest modulating frequency. Okay? A couple of other types of amplitude modulation. It is actually possible. Have a look at this signal. We've got an upper sideband and a lower sideband. Now, remember what we said, that all the information is contained within the sidebands. Now, it so happens with amplitude modulation like this, that the information in the upper sideband is exactly the same as the information in the lower sideband. So that brings the thing, you think, hold on a minute, we don't need both of them. One of them will do. Why do we need to transmit both of them? And one of them by himself contains all the information we need. No. Good thought, but no, it's not backup. We treat the whole thing as a signal. First time I've heard that, I'll have to remember that one. Yeah, so actually we could transmit just one sideband, and we call that single sideband. You might have heard of it as SSB. Okay, so let's just put this down and see what.
Single sideband.
So we can transmit single sideband.
ما في إلا أكتب يعني.
With carrier.
لا بس حلو اليوم صراحة.
عشان كتابة.
Sometimes this is called SSB. You might see that written down sometime. Now, how do we calculate the bandwidth of that? It's going to be less, of course.
Not the half.
Yes, it's approximately half that, isn't it? Because now the bandwidth is just from here to here, if it's the upper side band.
SSB.
Yes, or it's from here to here if it's the lower side band. So it's going to be half this. In other words, it's going to equal the highest modulating frequency. Not twice the highest modulation, just equal to the highest modulating. And if you look at that, that's exactly half this. Now, what advantage do you think that has?
Low frequency carrier, low frequency use.
Less
Not
band.
low frequency.
Less bandwidth.
Less.
Yeah, essentially it means if you can transmit all your information on a smaller bandwidth, you can get more channels, can't you, within there without interfering. So that's a big advantage.
More channels.
More channels without interfering. All the power saved in transmitting here can go into your one band. You see, so it's a bit more efficient. You're not spreading it between two bands. So you can see it, but the main advantage is a narrower bandwidth. And it's the same information. We're not wasting.
Can we transmit actually an SSB?
Can you transmit SSB? Yes.
You have to, when you isolate that.
One very simple solution to this is first of all generate in your transmitter this, and then use a filter to select one band, either your upper or your lower side band. That's the way it's normally done. And then just transmit that one band of frequencies, you see.
The advantage is save power.
Well, the main I'm going to list the advantages in a minute because I haven't discussed everything, but you understand the mechanics of what I'm talking about, physically what's happening. We either transmit this or we transmit that. We don't have to transmit both for the same information. Now, there are a number of advantages and disadvantages, but we'll talk about that in a minute.
You say how to receive the single sideband. First we send it as a sideband. And the receiving, we take only a single sideband.
Yeah, whatever we transmit, of course, that can only be received.
Okay, but you say we send single band, sideband, and receive single sideband.
Yes.
But how we send single sideband?
Well, this is the question was asked. Basically, in your transmitter, you generate this, and then you use a filter to select one of your, to select one of your bands.
The sender frequency of each band. You choose a filter.
You choose depending on, you choose a filter either for the upper or the lower sideband. You can choose either, and it will work.
Is there any difference between when you choose one and
Would be an advantage. I'll tell you where this is mainly used. This is used actually at HF communications. Yes, HF communications. And basically what happens is this. The operator can choose either his upper sideband or his lower sideband, okay, just by a switch on his control. He listens first. If he gets interference or he gets complaints that there's interference, he'll switch to the other band. You see? He might cut it. Yes, just the upper or the lower, that's all. Or lower. Yeah, if he gets interference, he'll switch to the other band, and maybe it will cut out the interference, you see. That's all.
more channels? I can see.
It's like more channels, yeah. You could think like this is like two channels in one, but
Once a single sideband, more channels we have in the...
you would, that's exactly right. Using single sideband, you can use a lot more channels in your band. Now, there are some variations on this. There is single sideband, for instance. Now look at this one. Without carrier. Now, there's an interesting one. Actually, there should be two R's in that carrier. I made a Interesting. This is called SSB with suppressed carrier. Suppressed, do you know what suppressed means? Means cut down. The power of the carrier is reduced. There's an interesting one. Very similar to this, except no carrier.
Yes.
It disappears. Right. What do you think the band? Is it going to change the bandwidth?
No.
Yes, there
Yes.
won't be any bandwidth.
Oh yes, we're still transmitting a sideband.
How are you transmitting it without any?
But there will be no lower or
عندك
higher,
يصير في
lower sideband,
The other side.
no B.
No. No. We still transmit a sideband, but we
Yes.
suppress the carrier. Now the bandwidth is simply the difference between the highest modulating
That's what I'm
frequency
saying.
and the lowest modulating frequency. Remember the bandwidth here was simply the highest modulating frequency.
Yeah.
Now the bandwidth here is slightly different. Yes, it's the difference.
15 in this case.
Yes, that's right.
This is something else. You don't see me long antenna.
Yes.
Very, very long.
No. It's still radio frequencies.
With K.
You're in a kilohertz.
No, we're in megahertz. What we're transmitting is frequencies between 99.505, which is radio, and 99.52, which is also radio. There's no kilohertz there at all,
But without carrier.
without the carrier. That's all we're
What
transmitting.
about phantasm?
You're transmitting that frequency, but there's no signal.
No, there is. What a lot of people get confused with this. They think, first of all, going back to what we were saying about the modulation, and they think about that, and they think, okay, now I'm going to remove the carrier. They think, okay, if you remove the carrier, the whole thing collapses. But in actual practice, that doesn't happen. All that happens is the shape of this signal changes. It's no longer an envelope modulation. That's all.
How does it normally look like?
It looks a little bit like this. Well, if I transmit, for instance, an upper frequency, let's say I transmit 20 kilohertz
Yeah.
modulated, then it will be a single sine wave, and that single sine wave will be 99.52 megahertz. If I transmit the lower frequency, 5 kilohertz, it'll be another single sine wave, and again another radio frequency of 99.505. It won't look like this.
This is FM modulation.
No, it isn't FM.
You're changing the frequency.
Because you're changing the frequency of modulation, but that's not the same thing as changing the type of modulation. The type of modulation is still amplitude modulation.
You're not. How are you going up or how are you going down? The amplitude is.
The type of modulation is amplitude modulation, but when you cut out certain frequencies from the output of the amplitude modulator, then the wave changes in nature, but it doesn't become FM. FM is where you change the frequency of the output according to the amplitude of the input. Here, you're not. The frequency of the output depends on the frequency of the input. So it's not FM, it's AM.
When you're transmitting.
All right. Say, for instance, I reduce the amplitude of this modulating frequency. Let's say I reduce the amplitude of the 20 kilohertz, right, down to 0. Zero amplitude. What do you expect this output to be?
The 20 kilohertz.
Yeah, 20 kilohertz. I'm modulating it, say, with 20 kilohertz, okay?
Uh-huh.
I'm modulating that carrier with 20 kilohertz. And then I'm suppressing a sideband and the carrier. What do you think the output will be? 0, exactly. Exactly the point. 0. No modulation, 0 output. The transmitter literally transmits nothing. And then the bigger the amplitude of your signal, the greater the output from your transmitter will be. Basically, all you're doing, if you consider your modulating frequency to be between 5 and 20 kilohertz, all you're doing is taking those frequencies and shifting them to that position on the frequency spectrum. That's what you're doing. And that's all you're doing with suppressed carrier modulation. That's what you're doing. It's like taking the same band of frequencies but moving them up to your radio frequency band.
So here see a single side band without carrier. Definition between highest and lowest.
Yes, in other words, if the high, like you were saying, if the highest is 20 and the lowest is 5, the difference is 15 kilohertz. So we've got 15 kilohertz here, 15 kilohertz here, but we've also got a little gap here of 10 kilohertz, the difference between the two low frequencies. So that gives me the total of 40 kilohertz, you see. Yeah, 40 from here to here,
Yeah.
15 from here to here, 15 from here to here.
You don't use the DC for the carrier. You don't use this side for the carrier. You only use the lower side band, the high side band. Then the bandwidth will be 30, not 40.
No, the position of the side bands, there's a gap in between of 10. In my example, in this example I showed here, you can't change that. You can't change that. What you're suggesting is 2 side bands without a carrier. Is that what you said?
I'm saying here, without the carrier, there's no band now. There's no information in this side. Let's see.
What I described here is this. That is this. 15 kilohertz in this example, yes. Yes, they're all amplitude modulation. I haven't spoken about any other type of modulation, just amplitude, but there are 3 ways in which we can amplitude modulate. This way, by the way, this is sometimes called, you might see in textbooks, this is sometimes called envelope modulation. And it gets its name actually from the nature of the modulation. Remember, it looks a little bit like this. That's the carrier modulated, amplitude modulated by the signal. Sometimes it's called envelope modulation. It's the simplest type. Early types of radio could only do envelope modulation. They couldn't do these 2. They didn't have good enough filters to do that.
On the last one, it's half.
This one here, actually I can draw maybe a little diagram here on each one, just as a reminder. This one is that, agreed?
Agree, yes.
This one is either this or this, agreed?
Yes.
One or the other. Do you see what are these little drawings?
Yes.
Okay, now this one is either this,
Joe, but without carrier.
yeah, without the carrier, or this. Now, whether it makes much difference on bandwidth depends on your lowest frequency of modulation. You know, that depends on that. It might not make a lot of difference. But you see the difference in each of these little...
The first one will be 40 kilohertz.
The first one, 40 kilohertz,
Another
20.
20 kilohertz,
15.
15 kilohertz, in that example I've given you, yes, exactly right. In those examples, that's exactly what it would be. Let's take a little break there. That has the information in it.
So the last one is the most clear one.
It is the most efficient one, but it's the most difficult one to receive. Now, there are some variations on this. Some transmitters, what they do is, they transmit what is called a pilot carrier. That is a very low-level carrier, which is in the receiver, the receiver selects that pilot carrier with a very narrow band filter and then uses that to synchronize an oscillator which generates the same frequency, and then that's mixed with the received signal to reintroduce the carrier. So you're right, we cannot really demodulate this without a carrier, but it's not actually necessary to transmit the full carrier. Now it does sound complex, and it is complex. It's not as simple as the original amplitude modulated wave.
This is now logical.
You can see how it's done there.
Yeah.
Good. But you can see also that these receivers must be a little bit more complex than a simple one like this.
No problem. How are you going to receive it? This was the problem.
That's right. You do need a carrier free. And indeed, this was one of the drawbacks. When they first started using this, you see, these types of receiver are quite complex, and they needed special filters, narrow band filters, to be able to select the band and to select the carrier. Very accurate oscillators. All this sort of thing was quite new when it first came out, and it was difficult to receive. Now it becomes a little bit more easy, of course. Okay, let's have a look at the advantages and disadvantages of each of these three types of amplitude modulation. The first one, the advantage of using the basic 2 sidebands and 1 carrier. This is what's produced when we envelope modulate our signal. Can anybody think of any disadvantage in using that?
High power almost.
What about bandwidth?
Low band.
No.
What about bandwidth?
Wide bandwidth.
Wide bandwidth, yes. It's not as efficient on bandwidth, is it? That's true. Not only are we wasting bandwidth, because we're transmitting 2 sidebands when we only really need 1 for the information, but also it's not efficient power-wise either. But in fact, the main disadvantage that I'd like you to remember is wide bandwidth. I'll just put that down here. And you should be able to see quite clearly why this bandwidth is wider than this and wider than this. And it's not necessary for the information. So what's its advantage? There's really only one advantage, and that is simplest receiver. Yeah, the receiver is very simple, and also the transmitter is quite simple as well. But simple radio equipment, shall we put? You'll find that all broadcast AM signals are this type. All of them, yes. When you tune to the AM band of your radio, to the MF band, medium frequency band, and you tune into an AM signal, it'll be this type of modulation. But when it comes to telephone communication, say on the HF band, or telephone communication on the MF band, which is used by ships at sea, then they might use one of these other 2 types of modulation in order to save space and to get a better, narrower bandwidth. But otherwise, very simple. In fact, all you really need to demodulate this is a simple diode, that's all. If any of you have ever experimented with simple radio receivers.
You cut the signal?
That's right, it's like half-wave rectification, isn't it?
You take a compressor.
Yeah, that's right. It's like half-wave rectification, or even, you can even have full. That's exactly what it is. A simple diode will demodulate that and give you the audio. Very simple. With a capacitor, yes, you need a capacitor to get rid of the RF, but the result is an audio output depending on the modulation. And it works very well.
And tune circuit.
Oh yes, I'm talking about just the demodulator now. You need the tune circuit to receive your signal, tuned to the particular carrier you're talking about. If you're going to make the whole thing, yes, of course. But the demodulator is very simple radio equipment indeed. So that's the advantage. The disadvantage is you're wasting a lot of bandwidth. Yeah, you've got twice as much bandwidth as you really need. It's disadvantage. Now,
I think a wide bandwidth, it is to use more energy or power. Why are you broadcasting to use it?
the reason why they broadcast with it is because of this. Anybody with even the simplest set can receive it. The oldest set can receive it still, for compatibility. All right, you can argue that it doesn't cost much now to produce sets like this, probably just as expensive as these now, but people have still got a lot of old sets and they still need to be compatible. You'd need a special type of radio receiver to receive these types of signals, you see, not just the ordinary one. Okay, and when we consider, of course, single sideband, SSB, then, of course, the main advantage is saving on bandwidth, isn't it? Narrower bandwidth. So that's its big advantage. And that's for the same amount of information. We're not losing any information there. Disadvantage, well, you need narrow bandpass filters. Now that might not seem much of a disadvantage, but again, we've got to go back to early radio sets to see that this was a difficult thing to achieve in practice. Narrow bandpass filters. Why do we need a narrow bandpass filter here? Because what we need to do is cut off one side. In the transmitter, we need to cut off one band, don't we? And in the receiver, we need a narrower band to receive the narrower band of frequencies. If this was a telephone channel, this would be approximately 3 kilohertz wide, wouldn't it? 3.5 kilohertz. And finally, of course, the single sideband without carrier. How much bandwidth is changed depends on the lowest frequency. So there's a little bit of bandwidth saving compared to this, but the main advantage is saving power in the carrier. If we reduce the carrier in our transmitter, the power that's wasted in the carrier can be put into these side frequencies. So it's more efficient. So I'm going to put here saving, the main advantage, saving power in the carrier. Very efficient. Because what happens with this, take this signal here, if you are speaking into the microphone, then what you're doing, you're modulating your carrier, aren't you? What if you stop speaking? The carrier continues to be transmitted.
Yes.
But here, if you stop speaking, this disappears. Nothing's transmitted.
Nothing.
It's quite efficient in that sense. But again, the disadvantage is we need to special receivers. Yeah, very special receivers. To inject the carrier. Inject means to put in back into place again what was missing, because like we said, you cannot really demodulate without a carrier. You've got no reference, and this is where it gets a bit difficult. All right, this is where it gets a little bit difficult, but of course we have a big advantage, very efficient in power, narrow bandwidth, but more complex receiver. Special receivers needed to inject the carriers. That's all I'm going to say on this. We're not actually going to do any circuit diagrams here, so don't worry about that. That's not part of our course.
Inject?
Inject, or to reinsert, to bring it back again. That was missing because it wasn't transmitted by the transmitter. To create it again. Use amplitude modulation, in our case, in Saudi, for HF communications, radio telephony HF communications uses amplitude modulation. We also use it for our